continue with the topic of adsorption, and today we will do some more problems so that you are completely thorough with the knowledge of adsorption. Consider a process where the adsorption follows a Langmuir isotherm. So if there is a Langmuir isotherm, obviously you need two constants. One is called the maximum adsorption, that is the Q max, which is given here 7.8 10 power minus 6, and then we have the constant, that is the constant which comes the denominator of the equation. So both are given. Now we are adding a feed of 1.2 liters which contains a protein of certain concentration, moles per liter of the protein. Now you are adding 80 cc of an adsorbent, and the goal is to adsorb as much of the protein as possible, and as I said it follows a Langmuir isotherm. So this is a Langmuir isotherm equation, Q equal to Q max multiplied by X, and that is the concentration of the solute which is in equilibrium with the concentration of the solute in the adsorbed phase divided by K plus X. So once you write the mass balance, the mass balance consists of, as I said before in the past 3 or 4 classes, the material coming in the form of the solute in the broth and the solute that is adsorbed, that should be equal to the concentration of the solute in the adsorbed phase. So W into Q, that where W is the amount of adsorbent we are taking in, that is given here 80 cc. Q is the concentration of the adsorbate that has been taken up by the adsorbent. This should be equal to F. F is the quantity of broth or slurry or solution you add, that is 1.2 liters here, multiplied by Xf minus X, where Xf is the concentration of the adsorbate in the feed and X is the concentration of the adsorbate after the adsorption process, okay, that is Xf minus F. So you are balancing these two, where Q is given by X into 7.8 into 10 power minus 6 divided by X plus 1.9 into 10 power minus 5. So you can balance these equation, and you see that X is appearing both in the numerator and the denominator, that means you need to solve it by trial and error. So it is slightly tricky, either you can do it by graphical method or you can use some computational tools, non-linear solution procedures. There are many softwares which can help you to do that, and thereby you can calculate your X, and so X comes out to be 3.9 into 10 power minus 5 moles per liter. So you are starting with that about 4 into 10 power minus 4 moles per liter of the protein which is adsorbed using an adsorbent, and the solution will finally contain 3.9 into 10 power 5 moles per liter of the solute. Now let us slightly complicate the adsorption process. Sometimes it is not possible to complete the adsorption in one stage, so you may resort to 2 stages. So like this particular figure, so you have a stage 1 where you have the solution containing the solute is introduced and you are adding a fresh adsorbent here, and then after you do the adsorption you may remove the adsorbent using filtration. Now you have this mother liquor or the broth, it is taken to a second stage where again you may add some fresh adsorbent and again you may repeat the same process. So this is a 2 stage adsorption process. You can have multiple stages, you can have 3, 4, 5 and so on actually, and here in each stage you are adding fresh adsorbent, that means Qf equal to 0, that means the concentration of the solute adsorbed that is introduced is 0, that means it is a fresh adsorbent, okay. So in this 2 stage process our goal is to find out what is the overall efficiency of the adsorption process. That means we need to do a mass balance here, calculate the concentration of the solute that is leaving, and then you do a mass balance here, and then you can calculate the concentration of the solute that is leaving the second stage, and by comparing it with the initial feed we can say this is the overall recovery efficiency or overall adsorption efficiency. Assume it to be a linear adsorption isotherm, we can extend it whether it is Freundlich or whether it is Langmuir, the same approach. So what is the mass balance here? We have 1 liter solution, so we convert that into Cc, the feed is 0.1 and what is the concentration of the solute leaving will be unknown x1, which is equal to 25 is the quantity of the adsorbent you are adding. Here we are assuming 25 Cc of the adsorbent, and normally you will be adding in grams, so you need to know the bulk density so that you can convert into volume as well. Now Q1 is the concentration of the solute in the adsorbent, which is given by this linear isotherm. So Q1 equal to 30 comes from here x1, so we can substitute this Q1 with this particular term and we can solve for x1 and we will get that x1 is equal to 0.0571. So the percentage recovery will be, you are reducing it from 0.1 to 0.057, so you just 0.1 minus 0.057 multiplied by 100 divided by 0.1, that comes out to be 42.8% efficient. So this particular stage helps you to adsorb 42.8% of the solute of interest. Now let us do the same thing in the second stage. So again you have the 1000, that is your feed 1000 cc's, and then the concentration of the solute entering now will be 0.571, right, and the next 2 is your unknown, and then again you are adding the same amount of adsorbent. You may add different amount of adsorbent, then you have correspondingly that number coming here. Assume in this particular problem we are adding the same amount like you added in the first stage. So again it is a fresh adsorbent, so there is no solute already present adsorbed on the adsorbent. So again it is equal to 25 into Q2, and Q2 is given by 30 into x2 here. So you see, look at these 2 equations, although they all follow the linear adsorption isotherm, the Q1 and x1 are related like this and Q2 and x2 are related like this, okay. So the equations here are very different. So you substitute again here and you can calculate for x2, say x2 comes out to be 0.0326. So if you compare 0.1 and 0.0326, we can find out the overall adsorption efficiency, right, that comes out to be 67.4%. So what it means is, if I have a single stage adsorber and the system follows a linear adsorption isotherm, the efficiency of adsorption is 42%. By adding another adsorber I am increasing the efficiency from 42 to 67. So please note that you are not adding 42 to another 42 and getting 80%, but actually you are getting only 67%. So if I add a third adsorber I may add another 10% maybe, if I add a fourth adsorber I may add about 5% and so on. So as we keep on adding extra stages, you are not going to dramatically increase the adsorption efficiency, but you will be just adding only small amounts of improvement. But then why do you add multiple stages? You need to add multiple stages if you are interested to adsorb as much of the solute as possible. Maybe the solute which you are adsorbing is a protein of interest for you, right. So you want to recover all the protein. So when you do it in one adsorption stage, maybe you are not able to recover, so you go to the next stage, you go to the next stage until all the protein is adsorbed. So you resort to this type of approach if the solute is extremely important for you, you want to recover all the solute, okay. So you get 67.4% efficiency by putting in the second stage. So you can have a third stage, you can have a fourth stage and so on. So in the third stage, what will be your linear adsorption isotherm equation? It will be like Q3 equal to 30 into x3. So in the fourth stage it will be Q4 into 30 into x4 and so on actually. So that is our assumption that the 30 remains always, whether it is Q1 x1 or Q2 x2 or Q3 x3, that 30 will always remain constant. So that is one of the assumptions when we do this type of multiple stage adsorption process, remember that. So that means the constant remains the same irrespective of the concentrations, because initially the concentration x1 may be very high, but later on x2 will be lower than x1, x3 will be lower than x2 and so on, but still we assume that this constant in the linear adsorption isotherm does not vary, generally that is what you assume, but in reality it may change and it may take different values depending upon the concentration of the solute which you are trying to adsorb. That means high concentration you may have different constant value, at low concentrations you may have different constant value, but in this particular problem we assumed that the constant k in the linear term remains constant, so do not forget that. This is called a cross flow system, that means the solution is flowing this way and your adsorbent is flowing vertically, so that is called a cross flow system. But let us look at another system, this is called a counter current system, that means your solution is flowing like this and your adsorbent is flowing from this way, second to 1. So solution is flowing from 1 to 2 and out, whereas your adsorbent is flowing from 2 to 1 and out this way, notice that. So if I have 3 stages, what will happen, my solution will be flowing from 1 to 3, whereas the adsorbent will flowing from 3 to 1. So this is called a counter current system. So let us look at this particular problem in counter current system. This is slightly tricky, you will notice why it is tricky later actually. Okay, so let us look at a counter current where the solution is fed here, again it is 1 liter and the solution contains 0.1 gram per cc of the solute concentration. Okay. Now the concentration of the adsorbent added is 25 cc, but the concentration of the solute on the adsorbent is not 0 because it is coming from stage 2 here, right. So it is not 0, please remember, so it will have some number, we will call it Q2 and then it is leaving the stage 1. Now let us go to stage 2. Now whatever solute is left behind from stage 1 adsorption enters the stage 2 and there is an adsorption taking place here. Now here the adsorbent is fresh, so there is no solute on the adsorbent here, so here you can take QF equal to 0, you see that, whereas in a cross flow system we took QF equal to 0 in both cases because you are adding fresh adsorbent, whereas in a counter current system because the adsorbent used in the stage 2 is sent to stage 1, it contains some amount of solute adsorbed, so here QF is not equal to 0, but here you are adding a fresh adsorbent, that is why QF equal to 0. So if you have 3 stage counter current system, what will happen, the adsorbent is added fresh in the 3rd stage, so only there you can assume QF equal to 0, whereas in other stages you cannot assume the concentration of solute that is adsorbed in the adsorbent as 0. Okay, so this is slightly tricky, let us look at stage 1 and do a mass balance. So 1000 cc, that is 1 liter, what is entering through the solution is 0.1, what is leaving is x1, so 0.1 minus x1, this is equal to 25 is the quantity of adsorbent you are adding in terms of volume, and Q2 is the concentration of the solute entering because of the adsorbent, okay, and Q1 is the concentration of the solute leaving the stage with the adsorbent. So you have Q1 minus Q2 here, right, and of course Q1 and x1 are related by the linear adsorption isotherm equation, Q1 equal to 30 into x1. Remember the linear adsorption isotherm or any isotherm will always have the concentrations from the leaving streams, not from the entering streams. So the assumption in a staged process is the streams that are leaving are in equilibrium, the streams that are leaving are in equilibrium. So what are the streams leaving here, Q1, x1, correct. So that is why you put q1 and x1, we do not put these two terms in this equation, we put q1 and x1 here, okay. So we can substitute q1 like this into this, okay. Now let us look at the second stage. So the concentration of the solute entering through the solution is x1 and what is leaving is x2. So 1000 into x1 minus x2 will be equal to, now here the adsorbent is fresh, right. So there is no concentration of solute entering because of the adsorbent. So that is why we add only one term 25 into q2 whatever is leaving, and again q2 equal to 30 x2. So you see again as I said the streams that are leaving a stage are in equilibrium. So q2 is equal to 30 x2. So now we can substitute q2 here and q1 like this. So you end up with two simultaneous equation containing two unknowns x1 and x2, understand. So two simultaneous equation containing x1 and x2. So we can solve and we end up with quantity of x1 is 0.0756, quantity of x2 is 0.043. So from point 1 we reduce the concentration of the solute to 0.043. So the efficiency, overall efficiency can be calculated, it comes to 56.7. If you notice the percentage efficiency from the previous problem where we used a cross flow type of design, this is a counter current type of design. So in the cross flow I got 67.4% recovery, whereas here I get about 56.7. So almost a reduction of 10%, right. Why is that? Because in cross flow we are adding fresh adsorbent at each stage, in counter current the adsorbent is sent from second stage to the first stage. So you only in the second stage you are adding fresh adsorbent. So the efficiency goes down by 10%, but the advantage is that you are using the same adsorbent, whereas in the previous design you are having 25 plus 25 50 cc of fresh adsorbent. So that means you are using up quite a lot of adsorbent if you want to use a cross flow type of study. That means if you are using too much you need to recover, recycle and again put it back, otherwise it is not very efficient. You can't throw away the adsorbent because the operating cost will be a function of adsorbent, unless the adsorbent can be just disposed of in the environment without causing any toxic hazard. Otherwise if it is an expensive one like zeolites and so on, you have to recover, and here in this design you are using 50 cc for one operation, whereas here you are using only 25 cc which is sent from second stage to first stage. So the amount of adsorbent you are handling in this counter current design is less. So economically it will work out cheaper if you are using very expensive adsorbent, okay. So for example if you are having 3 stages in a cross flow, you may have each stage if you are adding fresh you will be using up so much of adsorbent, whereas if you use a counter current type of design you will be using the same amount of adsorbent and extending it up for all the stages. Of course the efficiency goes down, as I showed in this particular problem. When you use a counter current the efficiency of recovery is only 56, whereas the other one comes out to almost 67. So efficiency goes down, but the amount of adsorbent you use is less. So for very expensive adsorbent a counter current is much more economical. Okay, let us go forward, let us look at a tubular adsorber. As I explained in the previous class, tubular adsorber contains adsorbent packed in a tube of varying length and of dimensions, diameter of varying diameter. Now you have the feed solution or feed gas entering from one end and it is leaving from the other end, and the concentration of the solute is 1.3 milligrams per liter. Assume that the system follows a linear adsorption with the K value, that is the constant value of 38, breakthrough happens after 6.4 hours and exhaustion at 10 hours. You remember the breakthrough curve? I hope you all remember the breakthrough curve. Initially all the solute gets absorbed by the adsorbent because your adsorbent is very fresh. So whatever stream that is leaving here will be devoid of any solute, there will not be any adsorbate present here, but as it gets saturated, slowly you will start seeing some solute in the exit stream, and that is called the breakthrough point. That is the point at which you start seeing the solute in the exit stream, and after some time the adsorbent is completely filled with the adsorbate. So it is not doing any job, whatever solute concentration that is entering will be exactly leaving, that is called the exhaustion time. Okay. So here in this problem the breakthrough time is given 6.4 hours and the exhaustion time is given as 10 hours. So you are asked to calculate the length of the adsorption zone, length of the and fraction of the bed used, fraction of the bed used at the breakthrough. Now let us recall how the breakthrough looks like and what is the adsorption zone and equilibrium zone. This is the breakthrough, the x axis is your time. So your graph starts like this and then it goes in a sigmoidal fashion and it flattens out. So this is called the breakthrough time and this is called the exhaustion time, and this region is called the equilibrium zone and this region is called the adsorption zone. Okay. So adsorption zone, how do you calculate that? The solute concentration is 1.3 mg per liter, the length is also 1.3 meters. So length of the column, 10 is your exhaustion time, 6.4 is the breakthrough time divided by the breakthrough time, that gives 0.73. I hope you remember these equations which we did couple of classes back. So the adsorption zone can be calculated as length into delta t divided by the Tb, where Tb is the breakthrough time. So delta t is nothing but difference between the exhaustion time and the breakthrough time. Okay. So 10 minus 6.4 divided by 6.4 multiplied by 1.3 gives you 0.73. That means 0.73 meters is called the adsorption zone, and then equilibrium zone you can subtract from the overall length, that comes out to be 0.57 meters. So 0.57 meters corresponds to the equilibrium zone and 0.73 meters corresponds to the adsorption zone. So what is the fraction of the bed used at the breakthrough? Again, if you remember, I taught you a couple of classes back, it is given by the formula 1 minus delta t divided by 2 Tb. Delta t is the exhaustion time minus the breakthrough time. Okay. So if you substitute these terms you get 0.72, that means 72% of the bed is used up when the breakthrough happens. That means 28% of the bed is not used up and when the breakthrough happens. Why is breakthrough very important? Because as soon as the breakthrough happens you do not want to continue the adsorption because some of the solute will start coming out in the effluent. So you would like to stop the adsorption process and regenerate your bed and then again bring it back into operation. So whenever you stop the adsorption process you are losing time. So ideally I should have the fraction of the bed used during breakthrough closer to 1, that means I will be, if I use more of the bed for the adsorption better it is. If it is less of the bed I need to keep on regenerating quite often, and as I said, if I want to regenerate I will be stopping my bed, I will be passing some gas or using high temperature to regenerate my adsorbent. So I will be spending money on the operating cost. So more the bed used up when the breakthrough happens better it is. That is why this particular calculation is very important, fraction of the bed used during at the breakthrough point, and here in this particular problem we find out that 72% of the bed is used up when the breakthrough happens. That means 28% of the bed is not used up, but still you will stop the adsorption process and regenerate your material. Whereas if you get less number, like instead of 72% you get 50%, then it is highly inefficient, because the remaining 50% of the bed is unused, and as soon as 50% gets used up you will stop your adsorption process and regenerate. So if such a situation arises, what do? You need to find a different adsorbent which is much more efficient. So you need to select adsorbent so that the fraction of the bed used up keeps going up and up, comes closer to 1, and higher the number better it is, 0.8, 0.85, then the number is very good, whereas 0.7, 0.6, 0.5 definitely it is not very good. Okay, let us look at another problem. We are having a feed solution of 1.2 liters and it contains 0.1 gram per cc of the solute. Okay. The solute is what we would like to adsorb with 20 cc of fresh adsorbent, and this adsorption process follows a Freundlich isotherm. Okay. And the Freundlich isotherm is given by Q equal to 32 x raised to the power 1 by 3, where x is the concentration of the solute in the solution equilibrium with the adsorbent. Again we can do a mass balance. So how do you do that? We can do 1.2 liters, that is 1200 cc, the amount of solute is 0.1 and the amount of solute after the adsorption process is x, so 0.1 minus x. Now this should be equal to the amount of solute that is present in the adsorbent, and initially the adsorbent is fresh, so you can just put 20 cc multiplied by 32 into x raised to the power 1 by 3. Now see, if you want to calculate x it becomes trial and error process, so we cannot directly calculate, so but we can still do a trial and error, assume different values of x and see whether we are able to solve it. And of course there are many softwares available nowadays which can also do it, but a very easy approach is possible, that is using a graphical method. Okay. So let us look at the graphical method. This portion I had told you before is called the operating line. Okay, this portion. So for different values of x on the x axis, if I substitute here I can get this number 1200.1 minus x. Okay. So it will look like this and it will be going down, sloping down, because we have minus x here. Okay. This is called the operating line. This portion is called the equilibrium, this portion 32 into x raised to the power 1 by 3, here put in 20. So this portion relates to the equilibrium here. Okay. So for different values of x I can plot two curves, the operating line corresponding to this side and the equilibrium curve corresponding to this side. So if I plot them both in a graph sheet and wherever they intersect, that will be the value of x. Very simple. By using a graph sheet I do not need to use a software package to find out the value of x. I plot this portion as a function of x which will appear like this, and I plot this portion as a function of x which will appear like this, and the point where they intersect will be the value of x here, very simple. So using a graph sheet we can immediately calculate x without resorting to any computational or a numerical technique. Otherwise we can use Excel and assume different values of x and then by trial and error calculate what will be the actual value of x. by solving this. So, even Excel can be used to do this type of solution, but most of the adsorption studies, if you have a graph sheet, you can do it very simply actually. And before the advent of computers, people used graph sheets to solve equations of this type. And if you have a equation like Langmuir, where you have x coming in the numerator and x coming in the denominator, again you can resort to a graph sheet to solve it, right. Let us further look at another problem. In the tubular adsorber, we some time back talked about a slightly more accurate approach to calculate the concentration both as a function of the distance z, or as a function of time. As the fluid flows, there is going to be adsorption taking place. As the solute gets adsorbed, the concentration of the solute is going to vary as a function of the length of the tube, okay, and it will also vary as a function of time. That is why you have an equation which has a rate of change of concentration as a function of time, and we also have change in the concentration as a function of z. And I also mentioned that this term comes because of the diffusion, where d is the diffusion coefficient. This term comes because of the bulk movement of the fluid through the column, and this term comes because of the adsorption of the solute from the liquid phase to the solid phase or the adsorbent phase. Okay, we can try to simplify this equation by assuming certain things. Suppose we assume accumulation is 0, that means the accumulation of the solute in the liquid phase is 0 because the amount of liquid present in the voids itself is 0, amount of solute present in the voids is 0, then we can neglect this portion. If we assume that the diffusion or the dispersion is very little, we can neglect this equation, right. So we can easily neglect these two equations. If we assume a linear adsorption isotherm, then Q equal to K x star, and rate of adsorption is equal to KL. KL is the mass transfer coefficient, A is the interfacial area multiplied by x minus x star. So we can, instead of x star, substitute this as Q by K. So we will end up with a linear differential equation. We can reduce the second order partial differential equation into linear differential equation like this: v dx by dz is equal to KLA x minus Q by K, and dq by dt is equal to KLA x minus Qk divided by 1 minus epsilon. So x will be a function of z and t, of course, because the concentration of x changes along the length of the axis as well as a function of time, and similarly q also will vary as a function of length of the column and time. It needs initial conditions at t equal to 0 at all locations along the axis q will be equal to 0 because nothing has been adsorbed. At t greater than 0 the fluid is entering, so at z is equal to 0 x will be xf, that is the maximum amount of adsorbate present at the entrance of the tube. Okay. So we can solve these using these conditions. The initial condition this is called, and this is called the boundary condition because this is at the entrance, so that is called the boundary conditions. Just like a stir tank adsorber, if you recall couple of classes back we did the stir tank absorber where we had a linear adsorption isotherm. We developed a relationship between X, that is the concentration of the solute in the stream going out of the stirred tank adsorber as a function of time, and similarly we developed another equation, that is the concentration of the solute in the adsorbent as a function of time. Whereas in a tubular design not only time comes in, the Z also comes in, because the concentration of the solute along the axis of the bed will also vary, that is why you have Z also coming into the picture. That is the main difference between a tubular design and a stirred tank design. Stirred tank, everything is stirred, so we have a bulk concentration, whereas in a tubular we do not have a back mixing, that is why the concentration of the solute along the Z axis also will vary, in addition to solute concentration varying as a function of time. So a stirred tank has complete back mixing, whereas tubular has no back mixing. Now you also have to consider pressure drops, because when you have a packed bed and when a solution flows through it, whether it is a gas or a liquid, when a fluid flows through it, because the fluid can flow only through the interstices, the packing material offers resistance, and so there is always a pressure developed. So the feed that is entering the packed bed has to overcome this particular pressure. So either it is achieved by having pumps, so that the pump can deliver enough pressure for the fluid to pass through it and come out through the other side, especially if the packing is very long, or if you have very small particles, then pressure drop will be very high. Now this pressure drop arises in many systems, especially in filtration. As the solids keep settling on top of the filter, the liquid has to flow through the bed, so there is a pressure drop coming into the picture. So initially there will not be any solid bed formed on top of the filter medium, but as time progresses the bed is formed, so the liquid has to flow through the bed and come out on the other side. So you need to have enough pressure for the liquid to flow through. Adsorber, like we have been seeing, a packed bed tubular adsorber, you need to apply enough pressure so that the liquid can overcome this pressure drop and come the other side. Packed bed distillation column, where you are distilling a mixture of liquids into various fractions, and if you have the column as a packed bed, then again the pressure drop will be tremendous, and you need to have the vapors able to overcome this particular pressure drop. Biofilters, where you are trying to remove toxic gases using a packed bed of microorganisms and nutrients, then again you have a situation of pressure drop. So in all these areas you need to consider the pressure drop, and the inlet pressure should be sufficiently large enough to overcome this pressure drop. Now pressure drop is proportional to many terms like bed length. If the bed length is very large, then your pressure drop is going to be also very large. Velocity, it will be a function of velocity, so if the velocity is large, pressure drop is large, velocity is low, pressure drop is low. Inversely proportional to tube diameter, if the tube diameter is very large, pressure drop is less, if the tube diameter is very small, pressure drop is high. So small tubes you will encounter higher pressure drops, large diameter tubes the pressure drop is less. Now let us look at a problem. Imagine I have a packed bed, bed length is 20 centimeter, diameter is 2.5 centimeter, bed volume is 70 cc, so it has got a pressure drop of 2 bars. That means if this side is atmospheric pressure, I need to introduce my fluid at least at a pressure of 2 bar, so that it can travel and come out on the other side. Now I want to increase my bed volume 1000 times, that means 70,000 cc. I want to increase the diameter 10 times, that is 25 centimeter. Now the question I need to answer is, what will be the pressure drop of this particular new packed bed when compared to the old packed bed. So the old packed bed volume was 70 cc, diameter of the tube was 2.5 centimeter. The new packed bed has a diameter of 25 centimeter and it has got a bed volume of 70,000 cc. What is the pressure drop? The pressure drop of the small setup was 2 bar, pressure drop of the large setup I need to calculate. Now you know bed volume, how do you calculate? Pi d square by 4 into length, agreed. Now the volume has increased 1000 times and the diameter has increased 10 times, that means the length will increase 10 times, right, because diameter has increased 10 times, that means diameter square, that is 100, length has increased 10 times, okay. So the diameter has increased to 10 times, the length also has increased to 10 times, okay. So the bed volume is 1000 times, diameter is 10 times, bed volume and diameter are related by diameter square, so this will become 100 times, so obviously the length will go up by 10 times. So the length has gone up by 10 times, that means pressure drop will go up by factor of 10, but my diameter also has increased by 10 times, that means the pressure drop will go down by a factor of 100, right, square. So because of the diameter my pressure drop will go down by 100, because of the length my pressure drop will increase by 10 times. So overall the pressure drop will increase 10 times, that means it will become 20 bar. Okay, so the current pressure drop of this particular unit will be 10 times the pressure drop of the previous unit. Now we have been talking for some time on something very important, that is called stage processes or a stage process. That means we assume an adsorption taking place in a single stage, we have a feed solution containing the solute, we have the adsorbent added here either in the form of a fresh adsorbent or already containing some adsorbate, and then two streams are leaving. One is the feed solution which has now lost some solute because of the adsorption process, and the adsorbent has collected some of the adsorbate. So two streams are entering, two streams are leaving in a stage, right, after equilibrium, and this particular stream and this particular stream that are leaving are considered to be in equilibrium, and this is called a stage process. And in a stage process solute is transferred from one stream to another. So in the adsorption what happens, the solute is transferred from the liquid to the solid, but in the desorption you can have the other way, the solute can be transferred from the solid to the liquid, that is the desorption. But something is happening, you have many streams mixing, there is an equilibrium taking place and the streams are leaving, that is what is called a stage process. And stage processes exist in many areas of downstream and unit operations. For example, if you go to extractor or extraction process, you have the solvent and you have the heavy liquid, the solvent and the heavy liquid are mixed together and the solute is extracted by the solvent, correct. So that is a stage process. Distillation, you have a vapor and a liquid, and the light material or low boiling material goes to the vapor phase, heavy boiling material goes to the liquid phase, again it is a stage. Adsorber we just saw, so the solute from the liquid phase goes to the adsorbent phase, or in a desorption the solute from the solid phase comes to the liquid phase. that is a stage process. Gas liquid absorption, where you have gas solubilizing into a bulk liquid like carbon dioxide in monoethanolamine, chlorine in sodium hydroxide, and so on. So recovery of many gases are performed in a gas liquid absorption process, and they are all based on solubility, and again this is also a stage process. So chemical engineers have been very comfortable with this type of concept of stage process. So adsorption, absorption, distillation, extraction, they are all called stage processes, and you can have multiple stages or single stage. So the whole process can be carried out in one stage, where you put in the two streams together, mix it thoroughly and allow it to equilibrate, separate, and the two streams leave. So the whole thing can be done in one stage, or you can do it in multiple stages. That means you allow it to separate, then you add some other stream, then again mix it, allow it to separate, then go to third stage, and so on. So you can have multiple stages. So things happen in each stage, there is an equilibrium that will take place in each stage. So stage 1 equilibrium is very different from stage 2 equilibrium, which will be very different from stage 3 equilibrium, and so on actually. So the assumption in this type of operation is that there is an equilibrium which takes place between the streams that are leaving the stage, and the equilibrium that is reached in stage 1 will be very different from the equilibrium that is reached in stage 2, stage 3, stage 4, and so on, but they all follow the same principle. So for example, like I explained linear adsorption isotherm, if stage 1 follows linear adsorption, so we can always assume that stage 2, stage 3, stage 4, everywhere you may have the same isotherm with the same constant values. So if you assume extraction taking place in stage 1 and the partition coefficient value is given in stage 1, we can assume that in each the other stages also same partition coefficient value. So it makes the life slightly easier, but the main assumption in a stage process is that the streams that are leaving are in equilibrium, and the type of process that is taking place in each stage is similar. So by doing this we can sort of rationalize many operations, unit operations. We can also extend knowledge from one type of unit operation into another type of unit operation. We will see that, especially when we go to the next topic of extraction, you will see very interesting mass balance and other calculations which will look like almost similar to what we studied in adsorption, and when we go to distillation you will see the same concepts coming into picture. So we can extend the various concepts you have learnt in one area of unit operation into another area, and so on. Actually that is the main advantage of grouping systems as stage processes. Another advantage of stage process, suppose I have a tubular reactor or a tubular adsorber, we talked about it a few slides back. You need to have partial differential equation because there is going to be variation in concentration across the length as well as a function of time. Now suppose I break the tubular reactor into many stages, 100 stages for example, or 1000 stages, and each stage I assume it as a mixed stir tank vessel, then the calculations, the type of equations becomes simpler, because in single stage like I talked about in a batch process, it is just material input equal to material output, there is no differential equation coming into the picture. So for each stage I can write a simple algebraic mass balance equation and I can solve it. So instead of having differential equations, by doing this type of multiple stages we can approximate a tubular vessel or a tubular adsorber, we can simplify our calculations, understand. Instead of having differential equations we are going to have many mass balance algebraic equations representing each of these stages, and it becomes much easier for us to solve algebraic equations rather than solving partial differential equations. And number 2, each of the stage process will have certain constants describing the principle under which it works, like in a extraction you will have something called partition coefficient, which is almost similar to a linear adsorption isotherm. So you have the two streams connected by a constant called K, and similarly in extraction you may have two streams connected by a partition coefficient. So the constants will appear to be almost similar when you move from an extraction to an adsorption, or to a gas liquid absorption, or to a distillation. So these are the advantages of rationalizing the various equilibrium processes as a stage process. And when we go to extraction or when we go to distillation, you will see how useful this type of knowledge is all about. Okay, thank you.